Welcome back, Physical Science. This is the fourth video in the 6.4 section. So we've looked at heating and cooling curves and calculating how the quantity of heat and the latent heat. So moving on to the last part of this booklet is just simply looking at water and its special characteristics. Now, if we go back to near the start of this whole section, we know that we have solid, liquid, gas, and most of the time we have solid molecules being very close together, closely packed. If it's in liquid form, it must have been heated up, so they're further apart, moving around quicker, and heated up even more. We have it in the gas form, spread out, and less dense. So less dense, going to liquid would be more dense. We have more molecules per unit volume. Then if it's solid, they're really compressed and extremely more dense than the liquid form. And in fact, if I was to put this into here, it would sink because there's more mass per volume. And that works with most substances, with the exception being water. And we'll look at its special characteristics here. So this part just makes mention of that. Most solids are more dense than the liquid form because they're more dense. The kinetic molecular theory says that the particles slow down, attraction happens, and they are closely packed. If you look at a water molecule, it looks something like this, though, kind of a V shape, or I like to use the term Mickey Mouse head, and it's due to the fact that we have here lone pairs of electrons on this side of the water molecule making it negative, and that automatically makes the opposite side positive. But as we see here, solid ice floats in liquid. So if we take a look at why, here we have water in a liquid form, molecules moving around. And an interesting thing here, and it's a lab that's kind of hard to get. We get mixed results with it, but water actually has its maximum density at 4 degrees C when it's really cold but still in a liquid form, because below that, what happens is that the negative part of a water molecule is attracted to the positive part of the molecule, and it gets into this structure, and you can see the particles of the water are further apart than in the liquid form. And there's a funky video here I have that illustrates that. Some really cool music, you're going to love it, but it kind of shows that happening here. So let's take a quick look at it. So here we have water just in the liquid form, room temperature, but it gradually cools down to 4 degrees and goes less. So you can see here it's cooling down and slowing down, and we'll see them interlock in that specific pattern. The music's getting really crazy now. Yeah, so there we have it, folks. So let me just get rid of that there before the next video starts playing. So we can see it interlocks when it slows down enough, and the solid form is actually less dense. It's not as compact as it is at 4 degrees C. So that's the interesting thing with water, because it's a polar molecule, and that attraction happens there. So that, and then over here I just mentioned that it being a water molecule being charged, etc., and that's why it interlocks. When you can slow them down enough, these forces come into play and interlock it. So here, and I just highlight that there. So the more organized molecules of water ice take up more space than the more disorganized molecules in liquid water, so water expands as it's freezing. And of course, before winter happens, it's a good idea to make sure the water is clear from lines, or prevent freezing pipes, because that expansion of water could cause pipes to explode, etc. All right, so that's the end of the booklet, folks. So it took 4 videos to get through it. So 3 states of matter: solid, liquid, gas. When thermal energy is released or absorbed, a change in state may happen. The change in temperature that occurs as a substance releases or absorbs thermal energy can be shown in a cooling graph or heating graph. Thermal energy that is absorbed or released during a change in state is called the latent heat of the substance. And remember, that word latent means hidden, so it appears to be hidden, but actually we're increasing potential or releasing potential energy as opposed to kinetic energy, which is measured by using a thermometer. So if the substance is melting or freezing, it's latent heat of fusion, or actually solidification or freezing. And if it's evaporating or condensing, we use the latent heat of vaporization value, or we can slap a negative on it, and it's the latent heat of condensation. Specific latent heat of fusion is the amount of energy per kilogram, so that word specific implies we're dealing with the kilogram amount, the amount of energy involved with that. And the specific latent heat of vaporization, again, this word specific implies per kilogram. The equation Q equals M times LF is used to calculate latent heat of fusion or freezing, and Q equals MLV is used to help calculate latent heat of vaporization or condensation if, again, we use a negative. And then ice is one of the few solids that floats in its liquid. This is due to the shape of its molecules and the forces of attraction between its molecules. All right. This assignment here, I'd like you to try all the questions. I'll give you some graph paper for number 2 so you can quickly graph that and answer the questions involved with that. So if you just quickly look at here, describe each part of the graph in terms of the states of matter. What type of graph it is. Is it heating or cooling? How can you tell? So there's a kind of 2 answers for this part A1. And if you look back, you'll see what I mean by that. There's kind of 2 areas where this could happen, so you could pick one or just simply tell both. Number 2, graph this heating curve, label the part, solid, liquid, gas, melting, evaporation, where does that happen? Determine the melting point and boiling point. So if you look back, you can see how to do that. Number 3, what would happen if you were to heat a liquid, water to 110 degrees C? So what would happen if water was at 110 degrees C? Would it be a change in state, or would it be in a specific form? Tell me about that. 4, explain the terms latent heat of fusion and latent heat of vaporization. What does that mean? To prevent fruit on trees from freezing and becoming inedible, fruit farmers in Ontario often spray their crops with water if they know the temperatures are going to drop below 0. Use your knowledge of latent heat to explain why this will happen. So think about what happens during freezing. If I have water and it's freezing, what is that water doing to the thermal energy? So think about that, and then you should be able to tell me why plants beside that freezing water may not freeze. And these last 4 questions deal with the calculations that we looked at. Calculate the latent heat of fusion for 2.4 kg of gold as it changes from molten liquid to a solid bar. So change in state there. How much thermal energy is needed to change 100 grams of ice at -20 into steam? Oh, there's that big question I was telling you about. It's water here. We're starting at a -20. Then it's going to melt. Then it's in the liquid form. Then it's going to vaporize, then reach that. So that actually hits all 5 parts of that graph, folks. So there'll be 5 calculations in that question. Number 8, while forming 1.5 kgs of aluminum statue, a metalsmith heats the aluminum up to 2700 degrees C, pours it in the mold, and then lets it cool to room temperature at 23 degrees C. Calculate the thermal energy released by aluminum during this process. So you're going to have to look back, figure out what is the temperature, what is the boiling point of aluminum, what is the melting point of aluminum, and then figure out how many sections of the graph will be covered. Then number 9, what makes water different from most substances, include a description of the physical characteristics. So you can look back at what we just talked about, and you should be able to handle that. All right, we'll see you again.